Hi, this is Fuchun from Imperial College London. I'm going to present some new results on leakage-resilient secret sharing. This is a joint work with Mahdi, Venkat, Ray, and Huaxiong. A symmetric key or public key crypto system is leakage resilient if the security still holds, even some information about the secret key is leaked. For information theoretic secret sharing scheme, since there is no secret key, one may wonder what is a meaningful leakage model. To get a quick idea of what is a secret sharing scheme, here is an example called threshold scheme. A secret is divided into several cells, and when enough number of cells coming together, reconstructs the secret. With even one cell less than enough, there is no information about the secret. Here are some existing leakage models. The most common leakage model studied is the local leakage model. The adversary can query a bounded number of full shelves, as well as querying a leakage function, an arbitrary function from each other shelf. And output a bounded number of bits. The adversary is only bounded by the number of full shelf queries and the number of output bits of the leakage function. The adversary is called long-adaptive if the adversary commits to her queries at the beginning of the game. A slightly stronger adversary, called partially adaptive adversary, can choose the leakage function according to the full shelf queries. Most of the known constructions of secret sharing, leakage-resilient secret sharing scheme are on local leakage. The strongest compartmentalized leakage model is the bounded collusion protocol. The adversary can query several times, each time on a bounded number of cells, and apply an arbitrary leakage function to these cells. The model is fully adaptive in that the adversary can choose subsequent choice of subset of cells and leakage functions according to the previous information. It turns out that the concrete construction in this model is a challenging problem. We conclude the background with the leakage-resilient results of Shamir Scheme. The Shamir secret sharing scheme can be interpreted as encoding a random message using the random matrix. the secret is represented as a finite field element. And then we sample some uniform finite field elements and do the vector matrix multiplication to generate the random cells. It is easy to see that with enough number of cells, we can reconstruct the secret and the randomness. A recent result shows that when the underlying finite field is of characteristic 2, Shamir scheme is not leakage resilient at all. Even with long-adaptive local leakage of 1 bit each cell using linear function, one can recover the full secret. On the other hand, another recent result shows that if the field is a large prime field, then Shamir scheme is in fact already leakage resilient against long-adaptive local leakage for moderate parameters. In this work, we start a systematic study of global leakage models and provide near-optimal constructions for some examples. We allow the adversary to access all cells at the same time. And in that case, we have to restrict the leakage function of the adversary. Otherwise, the adversary can reconstruct the secret and output the first bit. So we consider a structured class of leakage functions. And the adversary can choose an arbitrary function from the class and leak from all cells. We also consider long-adaptive adversary and adaptive adversaries. And an adaptive adversary can choose, for example, a leakage function to leak from the full cells, and then based on the information obtained to make a choice of full cells queries. And then based on all this information to choose leakage function and leak some more. Now is the question of what is a useful structure class of leakage function to consider. Secure multi-party computation is an important application for secret sharing scheme. In a secure multi-party computation, several people with private input coming together and try to compute a function of their private input without giving away extra information about their private input. This is done by encoding each of the private input using a secret sharing scheme and do the computation on the cells instead of the secret. Usually, the computation on the cells are algebraic functions. This gives a good motivation for us to study the algebraic class of leakage functions. We start with affine functions and consider both adaptive and non-adaptive cases. We also extend our result to low-degree polynomials, but the results obtained are less satisfactory. We also obtained near-optimal construction for local leakage as an independent interest results. Here's the technical overview. The idea of our construction can be interpreted as using a randomness extractor to mix the secret and the randomness of the Shamir scheme to make it leakage resilient. A randomness extractor is a function that maps a long uniform distribution over a bigger space to a uniform distribution over a smaller space. It turns out that we can have one function that works for a structured class of distributions. One example is the so-called affine source, which is a collection of flat distributions over affine subspaces. When the distribution is not structured and only bounded by the entropy bound, we have to use a family of extractor functions. These are called seeded extractors. Examples are universal hash family and depth over hash lemma. In our construction, we use the inverter of an extractor. An inverter of an extractor is a function mapping a uniform distribution over the smaller space to a uniform distribution over the bigger space. To make this happen, there is also an independent randomness input for the inverter. So we start with a uniform secret, and together with the independent randomness, we generate a uniform pre-image for the secret using the inverter of an extractor. And then this uniform pre-image is encoded using the Shamir scheme to generate the cells. And then a leakage adversary observed the output of the leakage function. Conditioned on this leakage, the uniform pre-image no longer has a uniform distribution. But if the extractor can extract uniform distribution from this distribution, then we recover the uniform secret. We started with the uniform secret and conditioned on the leakage. The distribution of the secret remains uniform. In this sense, the secret and the leakage are independent, which means leakage resilience. So depending on the leakage function considered, we use a corresponding extractor. In the case when the adversary is a local leakage adversary, since the leakage function for each cell in local leakage model is an arbitrary function, so we no longer have a structure in this pre-image distribution. In that case, we have to use a seeded extractor. Our results for affine leakage are near optimal. Intuitively, we construct a leakage-resilient version of the Shamir scheme. Recall that Shamir scheme is not leakage-resilient when the underlying field is of characteristic 2. Our result here can be understood as making the Shamir scheme leakage-resilient by using a seeded extractor. The leakage tolerance is the best one can hope for, since we allow the adversary to obtain a total amount of leakage, the total amount of information the adversary obtained is less than t-1 cell. Moreover, the secret length is equal to the cell length. This is the same as the original Shamir scheme. For adaptive adversary, we also have leakage resilience as long as the total amount of information obtained by the adversary is at most t-1 cells. But this time, we do not have optimal secret length. The secret length is a constant fraction of the cell length. For low-degree leakage, we only have a RAM scheme. A RAM scheme is a weak version of the threshold scheme. When enough of cells putting together, we reconstruct the secret. When one cell less than enough, we cannot reconstruct the secret, but we can obtain certain amount of information about the secret. It is only when t-g cells putting together that we have no information about the secret. G here is a gap. When the gap is 1, we recover the threshold scheme. The leakage tolerance is similar to previous affine case. We allowed it as long as the total amount of information given to adversary to be at most t-g, and the secret length is also a constant fraction of the cell length. We note that with the improvement on the underlying extractors, we might be able to get a threshold scheme with the gap equal to 1. It is also opened that whether we can improve parameters by considering a long-adaptive adversary and use a seeded extractor. Recall the local leakage model, a partially adaptive adversary It is recently shown that for local leakage model, the leakage ratio, which is defined by the number of bits output by the local leakage function divided by the shell length, is bounded for secret sharing scheme with full reconstruction. A secret sharing scheme is said to have full reconstruction if the reconstruction algorithm not only reconstruct the secret, but also all shells. Shamir scheme has full reconstruction, and so is our scheme. We achieve a leakage ratio that is almost equal to the upper bound. And the secret length is a constant fraction of the shell length. Thank you for your attention.